In this video, we're going to review some concepts in three-dimensional space and also some pre-calc ideas and kind of extend some of our pre-calc ideas to three-dimensional space. So, to begin with, sketch the points and find the distance. Instead of sketching the points, let's just talk about where they would be, okay? So this point would be, if I could just quickly draw the axes like this. Remember, we've got X and Y and Z. Like that. So this coordinate, -1, 2, 5, would go 1 unit back, 2 units over, and 5 units up. Okay? And this 3, 1, -4 would go 3 units in X, 1 unit in Y, and then 4 units down into Z. And the distance between them, remember, we simply use kind of an extended Pythagorean theorem where we do, the difference between the x's, so -1 minus 3, so -4 squared, plus the difference between the y's, so 2 minus 1 squared, and the difference between the z's squared. So we end up with 4 squared plus 1 squared plus 9 squared. It is the square root of 98. Okay, now find the equation of a circle with a center at 1, 3 and a radius of 6. This goes back to our pre-calc days. Recall that our basic formula for a circle is x squared plus y squared equals radius squared. And to adjust the center, we simply add kind of these parentheses. We say it's x minus 1 squared plus y minus 3 squared equals the radius squared, so equals 36. Okay. The last question on this kind of little review is find the zeros by completing the square. So I want to talk a little completing the square. Completing the square, if you remember, we began by kind of leaving a little space. Okay, I'm going to put kind of a blank there and put this minus 3. And since I want the zeros, I'm going to set this equal to 0. Completing the square, the goal is to create an algebraically simpler version of the parabola that is easier to work with and to manipulate. And the way we do this, if you remember from pre-calc, the way we complete the square is by finding half of the b, what we call the b value because it's on x, half of this and squaring it. So -3, so half of -6 is -3, squared would be 9. So we put a 9 here. Now, we're not allowed to just add 9 unless we subtract 9 here. So you can see now that we haven't changed anything because, of course, 9 minus 9 is 0. So adding 9, subtracting 9, we really haven't done anything to the equation other than create a way to collapse this down to a simpler x minus 3 squared. And again, the reason we know it's x minus 3 is it is half of this middle value, half of -6. So x minus 3 squared, if you actually multiplied that out, you would get this thing in parentheses. And now it is minus, because minus 3 minus 9 is minus 12 equals 0. So if I wanted to solve this for x, to figure out when it's 0, I could add 12 to both sides. I could take the square root. Of course, the square root, when we solve, we do a plus or minus square root of 12. And then I would add 3. Now, typically, I'm going to kind of just do this. We like to have the answer be with the root second. That's kind of the accepted way. So we would write that the zeros are 3 plus or minus the square root of 12. Okay? Finally, in three-dimensional space, describe the graph, region, or shape. Well, this first one, x equals 2. So remember again, let me just draw another quick little sketch here. We've got x, y, and z. Let's talk about kind of with a pointer what these would look like. If x was 2, so we come out along the x 2 units, this would simply be a vertical plane that passes through x equals 2. So I'm going to write a vertical plane, okay, through x equals 2. All right. The next one, y equals 5. So again, we go out along 5 units in y, and we would create this giant plane through y equals 5. And again, it would be a vertical plane. Sometimes you'll say, that it's also like parallel to a certain plane, like the x, in this case, the xz plane, it would be parallel to that. It's kind of nice. It tells you kind of what direction it is. Okay. And finally, the x equals, x is between 0 and 3. This simply is a block. It's a huge kind of block of, here's 0, here's 3. It is a huge kind of shaded region between those two. It's everything between those planes. So we say it's a huge volume or all of the planes between 0 and 3. So all vertical planes between x equals 0 and x equals 3. Or if you want to say all, like the huge block, the volume there between that, that would be acceptable as well. Okay, so I wanted to extend this idea. On the previous slide, we talked about circles. I want to extend this to spheres. And what you see a lot in three-dimensional space is that it's a pretty easy leap. Okay, so a sphere is simply going to be, whereas before we would have had just an x and a y, we would have done x minus the x coordinate squared plus y minus the y coordinate squared equals radius squared. Now it's simply going to extend to a z. So it's going to be x minus 1 squared plus y minus 4 squared plus z minus 5 squared equals, and it's still radius squared. So that's it. Okay. Next, I wanted to talk about kind of some algebra. And if you were wondering earlier why we include a little, or why I included a little review of completing the square, I really just wanted to get at, how do we look at a big ugly equation like this and manipulate it in a way that we know it's a sphere. And I'm going to just put this work right down here. So let me write it this way. X squared minus 4x. And I'm going to just use some parentheses. I'm going to leave a little space because we're going to complete the square for that. Plus, and then we're going to have y squared plus 2y plus, I'm going to leave a little space for that, and then we have a z squared plus 4z, and I'm going to leave a little space for that, and this is equal to 7. All right, so let's complete the square. Remember, it is half, in every case, it's going to be half this middle term squared, half this middle term squared, half this middle term squared. So half of negative 4 is negative 2, squared is 4. And if I add 4 to one side of an equal sign, I have to add 4 to the other. And this is a little different than the opener, because on the opener everything was on the same side, so I had to kind of offset it. I added 9, so I subtracted 9. Well, here it's more algebraic. I have to actually add it to both sides. Okay. Next parentheses, half of 2 is 1, squared is 1. So I have to add 1 over here as well. And finally, last parentheses, half of 4 is 2, squared is 4. So I add 4 here as well. So let's actually kind of collapse all this down. Then we've got x minus 2 squared plus y plus 1 squared plus z plus 2 squared equals 7 plus 4 plus 1 plus 4 is 16. Okay. So going back up, it says, does it represent a sphere? It sure does. We've found that everything is squared. This is the clue. And we've got it equal to this radius squared. So it says, well, what's the center? Well, x has been adjusted to be 2 units over. Y is 1 unit down, or 1 unit over, and z is negative 2. Okay, and the radius is 16. Now, next question is, if the radius, if this sphere hits the xy or xyz plane, what does that intersection look like? Let me drag this over and let me kind of show you what this thing looks like when it spins around. Okay, it's going to look like a circle. Okay, when it spins. Okay, so you'll notice right here when it turns, there, we see a circle when it hits the plane. So let me drag that out. It's a circle. Now when it hits the YZ plane, that means that x is equal to 0. So the cool thing is it says, what's the equation of this intersection? So what's the equation of the circle? Well, if I can kind of go down here, if I know that the x coordinate is 0, I could just plug that in. Of course, the rest is the same. So we'd say, okay, so this negative 2 squared is 4. So let me subtract 4 over here. So my final equation will be y plus 1 squared plus z plus 2 squared equals 12. So you'll notice this is a circle in the YZ plane. Okay, it looks a little weird because we're used to seeing them, of course, with x's and y's, but this should make sense. It doesn't need an x coordinate if it's not involving x at all. And if it's in the YZ plane, right, then it wouldn't need x. And it should also make sense that the center of the circle would simply be the projection on the YZ plane. You know, if I take the center of my sphere and kind of slide it back to the YZ plane, it'll be the center of the circle. That's the intersection point. So we still have these these points are important, and of course the radius must be smaller than the radius of the whole sphere.